Students, in the previous class, we have learned about the various types in it, various loads which are coming to the retaining wall. In this class, in this video, we are going to learn about the stability, how the how stable is your retaining wall for which you are designing, and with the soil force which is coming onto it. See the stability of the retaining wall. If you want to bifurcate, what are the types which are the probable failures if you are expecting from a retaining wall. First, what is your retaining wall should not overturn. This normally happens when you have a huge forcing. See, this is an overturning. So overturning normally happens when your active pressure is more than the self weight of itself, and the movements by these forces will cause the overturning. So you have a force here and you have an eccentricity from the base. So and if you multiply the force with the base, the height, then you'll get the movement. And you also have the weight of the section, or the empirical, or the normal dimensional section, normal dimensions, whatever you wanted to take. And if you calculate the whole weight, and you that weight is not at, at the center, it is eccentrically placed, and you also have a distance from its base. So if you calculate the weight multiplied by the distance, you will also get the moment, which are the resisting moments. So if the resisting moments are less than the overturning moments, then your retaining wall will overturn, and that should be normally the resisting moment should be 55% more than the overturning moments. So that is why you are always the dimensionless value, or the factor of safety, we call it as the resisting moments divided by overturning moments, should always be more than 1.5, which means that your resisting moments should be a 55% extra than the overturning moments. Here the overturning moments are the active earth pressure. So what is the resisting moments? Here the resisting moments are the self weight of the wall itself. So we do design our retaining wall based upon the stipulations which are given in the standard 456 code book. There was clearly mentioned, if you are taking dead load and an overturning movement, then if you are then you are doing the analysis and all those things, then zero point 0.9 times the moment resistant forces should always be greater than or equal to 1.4 times moment of overturning forces. This is what's given. So likewise, we do have for the other stability conditions. The second condition is sliding. So for in order to have the sliding, these are the conditions, and in order to resist that, as in the previous classes, in the previous video, I've shown you about the shear K. It is about all these things. How do we need to do all those things? So and we try to go into the problem how we do. This is we all have seen in the strength of materials. So the dimension is the basic thing. So in order to calculate the weight of the section, the proportions or the dimensions of the retaining wall, first we need to consider. We normally in any given problem, you only get the details of the soil in which you are retaining and the height which you are proposing. So based upon the height, will the proportions or some factors are 60% or 40%, we'll consider the percentage values, and then we preliminary assume the dimensions of the wall. Then we start analyzing the stability conditions of the retaining wall. And if the conditions of your retaining wall are stable, then we calculate those movements. And we if you are going for a limit state design, then you will calculate the steel as per limit state design. If the working stress is then I will calculate the steel as per working stress design. So these are all the dimensions which we normally follow. So I don't want to read them also because you have them. If you wanted to have, you can note down. So this is the main thing. If you want to introduce the steel, normally this is the advanced concrete design where we the only two metals which we talk about in this subject is concrete and steel. So uh, your retaining wall where normally we provide steel where tension occurs and we ignore the steel in compression because concrete is very good in compression rather than providing if you still provide in compression zone also the economy which you talk about it's not um, you're not doing the good judgment to economy. So the figure shows the thick line shows the stable condition of a retaining wall, and if you're not reinforcing it, the dotted line shows the deflected shape or the deformed shape of your retaining wall, and you can see the fibers over here are tensioned, and the fibers outside are tensioned, and the fibers at here are tensioned, and now the fibers at here are tension and the fibers at the heel outer upper are in tension and at toe are at tension. So the these lines will show you the provision of or where the best way of providing the steel where you could resist the steel, all the tension forces are resisted by that. So it just you can bring this cantilever a slab kind of a thing. So normally we do design the stem calculations, then we do toe calculations, then we do this heel calculation, and based upon their movements, relevant movements, we calculate the steels and we just detail them. So these are the main things which we need to uh, do the design in cantilever slabs. So the movement which is coming onto the stem, which we calculate is like what gamma is the density, gamma h cube by 6 into ka. This is in kilometer per meter square. Here he is given in different units, but SI units kilometer per square meters. And if you are following a balanced section, the mu is given by qbt square. So if you can, or if you wanted to go for a another reinforced section, then you can go 0.87 FIST minus FIST by FCK. This is available in IS for based upon the steel values. We calculate the spacing. The curtailments of the bars is when you go for huge heights, then the curtailments at a certain height will cut the steel, and after that we extend the bar. So why we do is when you see the pressure diagram here, it is a triangular vary. So if you are getting an area of 333 here, it doesn't mean that you need to provide 333 here because the force here itself is very small. So you can curtail the your 300 the steel whatever you are providing to certain height. So that what is that certain height and to which height you are cutting the bar is what we call as a curtailing bars, and that formula is given by this AST1 by AST2, which is approximately equal to H1 square by H2 square, where AST is the area of steel in the below section and AST2 is the area in the above section, and the height is not from base, the height is from top. So yeah, up to what height and h2, see h2 are overlap to certain height here in the diagrammatically represented at the bottom, but it's not, it's so at a certain height will contain a bar and the full height will extend it. So there is a bit of reduction in the steel reinforcement. We can bring down the the amount which we spend for this tail. So every alternative bar, for example, if 230 square, I'll show you in a with the sketch. Okay. So the first bar goes, and the second bar it will go to the full height, and the third bar goes to certain height, and fourth bar goes to the full height. So so on continue. So every alternative bar we cut it. So now you have an edit. So this is a ST1 and this is AST2. Thank you for listening. I hope you understood the design of Red Animal.